But the first thing you want to do here, which I always find to be easier, is to convert that into a mixed number. This is one of the very few times that mixed numbers make sense. So 7 goes into 24 how many times? 3. There's 3 and 1/7 pi left over. We okay with that? There's 3 and 3/7 pi. Just making sure. Good job paying attention, ladies. Good job. So, so with this one, what I want to do then is first of all, as I look at that, is this angle greater than 2 pi to start with? It is. So what we have to do to get positive and negative coterminals is that I have to first of all figure out what it is within 1 revolution, and then go from there. Now it works out nicely is that when you're over 2 revolutions, first thing you gotta do is count 1 little, 2 little, 3 little pi's, and then when I'm at 3/7 pi, is that here's halfway. Halfway would be here. Is 3/7 more or less than halfway? That's less. So 3/7 is down here. Okay. How far down did I move off of the pi value to get to that? 3/7. Because that's by doing that. Okay. So this 3 pi over 7, and I know we've been talking about what that means. Whenever you move something off of the x-axis, it's called the reference angle. Reference angles are going to be huge. We always use what's called reference angle. We always measure off of the x-axis. This one we move down 3 pi over 7. So that's where this one gets placed. So to get a positive coterminal angle, I just have to go 1 pi and 3/7. So 1 and 3/7 would be 10 pi over 7. Thank you. To go negative, I'm moving the other direction. Okay? I'm moving the other direction. If I think about it, a full revolution of negative pi would be here. But I need to back it out 3/7. So technically this would be negative 7 pi over 7 pi. I went the whole way to here to be negative pi. But I had to move it down 3/7. So my negative coterminal would be negative 4 pi over 7. Okay. It's the idea that you always want to figure out how far you are off of the x-axis because you can do those little tricks. Okay. I didn't specify not to do that. So from here on out, don't do that. Okay. From here on out, when you start rating, you want to keep ratings because believe me, in the long run, it makes everything so much easier. Okay. Nina, you had a question. 64? Okay. 64, that one. Is that the 3? Oh, okay. So in 64, the formulas that we talked about yesterday for arc length and for area, it meant that theta was always given in radians. So in this case here, if I want to find the arc length of this one, arc length is just theta times radians. So I need to convert this into radians. Well, to do that, I take 120 over 180, slap a pi next to it, and then I multiply it times 5. Okay. So I simplify my fraction, 2/3. So I get 10 pi over 3 arc length. Devin, you okay? Okay. And then then I do the same thing with the other was 1/2 theta r squared. So we do the same thing. It's 1/2. Oops. And it was 5 squared, and then again 120 over 180 times pi, which we already knew that wound up being 2/3. So we get 25 times 2 times pi over 2 times 3. So you get 25 pi over 3 units squared. Because this is, I just simplified out. Because we just did it. I just rewrote it. Does that make more sense? Yes, sir. I'm sorry. No. Exact answers. Oh, you don't need to calculate. Okay. What else you got? You'll be okay without a calculator, don't worry. That's how the formula is found. When that is the answer. They gave you the problem in degrees, but in order to solve it, your answer winds up in radian. Oh, I would just write 50.
Oh, okay.
I would.
Okay, I just made you.
Your answer, because you have 25 times 2 over 2 times 3, so it winds up being 25 pi over 3.
Okay.
Because when you did this last year, when you did this problem last year, you had 120 for your degree. What you did was this: angle over 180, or sorry, angle over 180 times 2. Sorry. You did that for arc length. What I want you to see is that this year it becomes angle over 180 times pi times r. This value here is how you convert a degree into a radian. So by doing that, you're automatically switching into radians. Because that's what it means. This value here is. Oh, and you were thinking because a theta was given to you as theta. Oh, I didn't even realize. I didn't even think about explaining that. I'm sorry. Okay, so guys, yes, now I know why you're going like that. All right. So in these problems here, I see why you guys were saying theta was in degrees. Your answer, in order to do any of this stuff, it has to go into radians. Okay, so that's why if you just did theta times radius, is that what you did? Okay, I'm sorry. I didn't make that clear enough, I guess. I apologize. I honestly didn't realize that they wrote theta there. I thought they meant that their angle. I didn't catch it. And I teach this for how many years? I didn't even notice it until just now. So yeah, you have to convert degrees into the radian to make it work. Okay? Sorry about that. But it's not hard to do though, right? Any others on these? All right, make sure your name. Yes, sir. Which one? 60? Sure. 3 pi over 4 and 9 pi over 8. I'll show you. Sorry. This is already given to you in radians, so you don't have to do any conversion. So the first one is for arc length. It is quite literally 3 pi over 4 because it's just radius times theta when theta is in radians. I'll say that. So the other one would be 1/2 radius squared times theta when theta is in radians. Well, theta here is pi over 4. That's where I got 9 pi over 8. Okay. Jarzewski. Which one? Sure. Okay, we got a minute here. Before we have a couple things to talk about and show you something real fast. 40. Positive, negative coterminal angles when you are in radians again. Now, first thing you want to do, since this is a top-heavy fraction, I want to figure out what does this look like in terms of a mixed number, because it's going to be easier to place it. Okay? What I mean by place it, I mean by putting it on a graph so we can figure out where everything goes. So how many times does 2 go into 13? 6, and how much is left over? So 6 and 1/2 pi, and that's what it would be considered in terms of a mixed number. So we count. You ready? 1 little, 2 little, 3 little pies, 4. Come on. You guys are helping. Come on. Ready? Here we go. 1 little, 2. I can't hear you, Devin. 3 little pies, 4 little, 5 little, 6 little pies. Now I have to go. Where is 1/2 located? Very good. So I need to figure out where is that located within 1 revolution. It's at 90, it's at pi over 2. The reason that I can do that is because if I back out 2 pi, if I back out 2 pi 3 times, I'm left at pi over 2. And that would be my within 1 revolution as a positive coterminal angle. Okay? Now, if I go the other direction, here's negative 1 pi, add another negative half pi, and I wind up at negative 3 pi over 2 going the other way. Okay. What's wrong, Nelson? Stand up. Seriously, stand up. You don't need to know the numbers. Stand up. Now, actually, you should probably stand up here so Devin can see you. Come here. Hey, Devin. Do you know Miss Nelson? Get closer. Do you know her? Okay. She's nice. Anyway. All right. So right now we're facing that way. Okay. I want to turn 90 degrees to your right. Let me look at the door. So when you're looking at the door, what I want you to do is I want you to spin around 2 revolutions. 2, thank you. 1, 2. Are you facing the same spot? Okay, go around one more time. Are you still facing the same spot? Okay. So what you did is you started facing 90 degrees and you spun around 3 times and you're still facing 90 degrees. Okay, now go the other direction and wind up where you were at. Are you still in the same spot? All we're doing is we're spinning around to get to the same position every time. And what happens is by spinning, if you know where you're starting at, guys, if I know that I'm moving up here, we'll just say that this is 60 degrees. And in order for me to get back to here, I have to go all the way around. That's 360, and then add 60. So if I add 360 to that, now I'm at 420 degrees. Now if I go the other way, that's 180. That's 270. This is 60 degrees off of negative 360, so this is 60 degrees off. That means how far did I have to go negatively to get to here? If I'm the only thing that's changing here is that I'm adding and subtracting pi. So if I start at 3 pi over 4. Where's that located? Where's it located? You tell me. 3/4. So here's 0, here's 1, here's a half. Where's 3/4? Okay. How far are you off of the x-axis? How far are you off the x-axis? Okay. So I only have 1 pen. So I'm only 1/4 off. Okay. So if I came to here, to get back to this spot here, what would I have to add this to get back to that same spot? To go from here to here, what do I have to add? 2 pi. Okay, so if I add 2 pi to this, if I want to get a denominator of a 4 and have a numerator that it equals, there you go. What's 3 plus 8? Okay, if I wanted to go this way, I'm going to take, and you get, see how much easier that is? Don't overthink it. Don't overthink it. You're overthinking it. Don't. Yeah, like I said, make sure your names are on it, pass it up. I wanted to talk to you guys about a bill again. Kevin, I totally forgot to send a unit circle to you. You can just make a circle and fill in blanks, and I'll send you a filled in one tomorrow. Okay? I'm sorry. Don't hate me. It was Bradley's fault. Yeah. Is there a spare? So one of the things that happens as we get going into this stuff, it is, I know we kind of briefly talked about this yesterday with the whole setup of the unit circle. And what I wanted to do today was make sure that we get a good build. Okay. And what I wanted to show you guys was what exactly are all the extra little bits and pieces that we can get into here as we go along. Now, yesterday we drew a rough sketch of this by hand. I'm like, make sure you got space, blah, 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 I'm there. Today I figured that if I give you an actual hard copy, pass around the 3-hole punch or staple key to throw in your desk, that we can do something like that. You go from here. Whatever, just probably not to your face. So yesterday we did this. We started at 0. If you went all the way around the circle, where did you wind up at? 360. And if you recall, yesterday we talked about building this in via halvesies. So what was half of 360? 180. What was half of 180? And then if I add 180 to 90, I get 270. Okay. Also with that, we switched all of those guys right away into radian measure. If we started at 0, we went full circle. How many radians was that to go full circle? 2 pi. So we said that was 2 pi. Half of 2 pi is, half of a pi is, and then if I add a whole pi to a half, I get 3 pi over 2. And when we did that, that's kind of where we went from there. Then we switched back to degrees again, and we went to the 45s. If I'm looking at my 90-degree angle, what's half of 45, or what's half of 90 degrees? 45. It's not my phone shape. Yeah, I don't know whose it is. And then from there, remember how we broke it down. We went from 0, 45, 90. What was 90 plus 45? 135. Add 90, add 45, you got 180. Then we had 225, 270, 315, and 360. That's how we were able to count all of the angles by 45 degrees. When we did that, we also said that 45 degrees, since 45 degrees was half of 90, well, then we said, well, that has to also be half of whatever the radian value is. This is why we can't have nice things. So what was half of a half? 4. So at 45, we had pi over 4. Remember how we started counting? We counted by fourths. We had 0, 1/4, 2/4, 3/4. 4/4 gave us the whole. 5/4. 6/4 simplified to the 3 halves. And then 7/4. And lastly, 8/4 for the 2. And that's how we built that around with the 45s. Again, you guys didn't seem to be super upset or crazy about how we were working that through just by working with halvesies and so it wasn't too difficult. After we did that, then we said, well, the other relationship that we could get into was with 90 and 30. Well, excuse me, we know that 30 degrees is how much of 90? It's a third. So if we count up by 30s, we had a 30 degree, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, and 360. And that was another little shortcut into there. And I believe yesterday at this point, I showed you guys, hey, remember all that talk and stuff that we've done all last year in geometry and a little bit of so far this year about this whole special right triangle stuff? Gee, guess what just happened? Here's special right triangles. Now, at this point, we also switched all of those into radians because we know that since 30 is a third of 90, we know that the radian measure has to also be a third of a half. So what is 1/3 of 1/2? 1/6. Good. Remember, just multiply out. And remember, I'm just not saying what is 1/3 of pi over 2. I'm just saying it is a half because we know the pi is going to have to be there. So what we're going to do here, for every 30 degrees, you are moving up 1/6. So we said that at 30 it was pi over 6. At 60 was 2 pi over 6. Right? Yeah, 2 pi over 6, but we wrote it as pi over 3. So we have 1, 6, 2, 6, 3, 6, 4, 6, which is 5, 6, 6, 6 gives us our whole. 7, 6, 8, 6, which is 4 over 3. Yep. We have 8, 6, 9, 6, which is 3 halves. 10, 6 at 300, which is 5/3. Very good. And then lastly, 11. 6 because 12, 6 brings us back up to 2. Okay. From there, we were able to just kind of say, okay, this is where everything kind of goes. I don't know if we got any further than that yesterday. So let's take it a quick step further because it's pretty easy. When I'm looking at the quadrants, do you guys agree that we have quadrant 1, quadrant 2, 3, and 4 as you go around? Okay. In quadrant 1, what values are positive? X's or Y's or both or what? Okay. So in quadrant 1, I know that they are both positive. What's positive, what's negative in quadrant 2? Negative X, good. Negative X, oops. Negative, positive, and then it goes negative, negative, and then lastly, positive, negative. And those were things that you guys learned when you first learned about how to plot ordered pairs. That was not very difficult to look at. Now the fun part. I know. Yesterday we talked briefly about that thing called a reference angle. Remember, a reference angle is how far something is placed off of the x-axis. If I'm placed here, my angle is 30. If I'm placed here, how far off am I of the x-axis? I'm also off 30 degrees. If I'm down here, I'm off by how much? 60. And that's the idea. You're figuring out how far you are off of an x-axis. That's what you do with a reference angle. Well, let's go and say we are at this 30-degree angle. And if I'm at that 30-degree angle, if I drop a vertical, what do I create? A 30, 60, 90 triangle. When you have a 30, 60, 90 triangle, what value is opposite your 30? Okay, you're right, it's q. Remember you guys did q root 3, and 2q? Can I just say that it's 1? You okay with that? So if opposite my 30 is 1, What's my adjacent? Root 3. And what's my hypotenuse? 2. Okay. Now, if I'm looking at that, that root 3 is representing some sort of a horizontal approach, isn't it? That 1 is some vertical thing, isn't it? Now, when you're dealing with trig functions, what function works with the horizontal? Think about your adjacent. What's next to you? Cosine, and what's vertical? Sine. So that means that the sine of 30 would be 1/2. The cosine of 30 would be root 3 over 2. Well, if I want to get root 3 over 2, isn't that just going to wind up being, that's my x coordinate there. What comes first in the alphabet, cosine or sine? Cosine. What comes first in the alphabet, x or y? Cosine relates to your x values. Sine relates to your y values for your ordered pairs. For your trig functions upon the unit circle. When you're at 45, if I'm at 45, it's 1, 1, root 2. What's my cosine of 45? 1 over root 2, but we write it as, bless you, root 2 over 2. What's the sine? Root 2 over 2. Oops. What's the cosine at 60 then? What's that? That point is at where the terminal side hits the circle. That's the ordered pair at that point. There's a reason why we're figuring that out. What's the cosine of 60? 1/2. Good. And what's the sine of 60? Root 3 over 2. So we're at 1/2 and root 3 over 2. Now, when things start to get kind of interesting here is when you move these into the other quadrants. If I take this 30 degrees here, and I move it horizontally here, when you move things horizontally, what doesn't change? The y value. What's the sine of 150? It's 1/2. It's the value of the y value. So when you get over to here, we have 1/2 is its y value. What do you think its x is going to be? It's going to be negative root 3 over 2, because remember, when you get placed here as a 30 degree, what went negative? What went negative here was my negative root 3. My adjacent moved negative. My vertical is still 1. My radius is still 2, as it still goes around. So my sine is opposite hypotenuse because it's a right triangle. So my y value is still 1/2. Hey, Devin, the worksheet's posted. Do the odds. The adjacent is my x value. That's why my cosine value is negative. Yeah. Oh, you can just, if needed, write it in simplified radical form. So in case if you need to write it in simplified radical form. Okay. If it didn't work out like that. It usually, I don't know how airplanes fly, but maybe. I don't know. You might have to think about that. I can't tell you. Okay. What do you think happens with all the rest of them? Exact same thing. The exact same thing happens all the way around. If I take this value here and I move down 30 degrees, what becomes negative here? They're both negative. So think of it this way. If sine is going to be negative 1 over 2. Cosine is negative root 3 over 2. What's the tangent going to be? Negative 1 over negative root 3, which is root 3 over 3, and it becomes positive. Because, yep. So your ordered pairs here, guys, this is rather large that you have to listen about here. As you're walking through this, your ordered pairs, their signs, S-I-G-N, just change. It never varies from those three triangles. Those three triangles just get reflected into the different quadrants, and their positives and negatives just switch. So here you get negative root 3 over 2, negative 1/2. If I moved it over here, I'd have root 3 over 2 and negative 1/2. And it goes around. It works for all ordered pairs. Yes, sir?
Why is the y value 1/2?
Well, when you're looking, if you look at your
Side is 1.
correct, but we are talking about with the angle thrown in there. So there's a specific, because as it's moving through, it's not at 1. If it was at 1, it would be a straight vertical shot at 1. Because 1 is going to be located at 1, 0. Because it comes out 1 unit, and as it's moving in, it's further in from a 1. Because if you look at a square, this would be 1, 1, negative 1, negative 1. See where I'm going with that? So it's moving inward from the arc. So the x values and y values are going to change. Does that make sense?
Yeah.
That's a great question. That's a great question. We'll get to quadrantal stuff tomorrow. Okay? And like I said, you guys can go through. Oops. As you go through all of those ordered pairs that were in the first quadrant, as they reflect into the different quadrants, just the signs change, the SIGNs, not the SINEs. Okay? That's how all of this stuff is going to work. And it all stems from the idea of what we call a reference angle. And I know that I've been saying that word, and I've been showing you what it is. And as you go through these problems, as you get into this further and further and further, because we'll spend more time on this tomorrow, because I wanted to talk a little bit about a couple of things real quick, is that your reference angle is always how far you have bounced off of an x-axis. Okay? I just want to make sure we were clear with that. The other thing I wanted to just kind of reiterate with you guys, and I know a lot of teachers will be talking about this, whether you've heard about it today or you'll hear about it more tomorrow. They are doing a full lockdown drill on Thursday. Okay? So it's different from what had happened a couple weeks ago when it was kind of like a, hey, let's just close the doors and continue teaching and all that for an extra hour. They're actually going to do the whole, not like say, hey, there's an intruder in the building, but they're going to put us all into lockdown, shelter in place type thing. There's different variations of all that stuff, and believe me, I know that we're right next to these doorways, and it's kind of a crappy place to be because those doors don't technically always lock right away, and they're easily broken into and all. But basically, with us, we would just kind of get it over in here. Okay? If we needed to get out a window, we could get out a window. That fall's not going to kill you. It might hurt your leg, but we'll throw Bender out. We'll throw Bender out first. What's that? No, because there's grass off the side. Because you're not going to jump out the window. What you would do is you hang underneath and you just let go. Yeah, you're tall. You've got less to fall than somebody else. But just guys, it is kind of a crappy situation nowadays. We have to talk about stuff like this. It's awful that we have to have these conversations about what do you do if the worst thing happens. Basically, we're going to preserve and do whatever we can to get through it and or get the heck out of here. Okay. We talked about this a lot last hour in my geometry class. They had a ton of questions about stuff, about evacuations and things like that. It's the best thing I can tell you is that I know that I've heard that it's supposed to be third hour. It's either second or third hour on Thursday. I know that it's whatever you do when you get into these drill things, I know we're all kind of, but you don't want to have to not know what to do in case something ever does happen. So just listen to your teachers, listen to whomever's there, and go through it, and just kind of think about it for a second of, okay, I don't ever want to have to practice this for real. But as we've all seen, it's happening. It's happening a lot, and it sucks. And trust me that I want to get through anything just as much as you guys do, because I wouldn't want anything to happen to you guys or myself either. It's just, it's terrible to have to talk about it, but just do me a favor, because I know you probably, I won't be during this class period, I don't think, because I know that. Whomever you're with, just give them attention and, take it for what it's worth. They say cover your head and hide in a corner, do it, just be quiet as best you can. If you have questions about stuff, about what to do in a specific room, if your teacher's not sure, ask somebody, things like that. I know that you're not supposed to listen to what they say on the intercom, because if it's a lockdown, the actual, Lockhart or Second Jackets will come around and they'll unlock the doors and tell you, hey, your guys are okay, as opposed to people still trying to get in and kind of say, no, you got to go. Things like that, but kind of the world we're living in nowadays, but just take it for what it's worth and really think about what you would do and what you have to do and those kind of things. So, I hate telling series. But believe me, if anything ever does come up and things like you guys need to know or anything like that, believe me, I am one person who will always tell you what is going on, just because I would want to know as well. So you can believe me if something ever does, if you're not sure about what happened during a day, something weird did happen. If I know anything, I would tell you, because that's what I do. So things like that. Other than that, I don't know. Do you guys have questions about any of that? And it's heavy and it's late and things. Well, don't lose that sheet. We're going to kind of reference that pretty much for the next few days. People have always asked this, do I need to memorize this? No. There is absolutely no reason to memorize any of this stuff. If you know your alphabet, that cosine comes before sine, and you know that x comes before y, and you can draw those two triangles real quick, you can reference anything as we go along. And we're going to do a ton of stuff off of this. You're going to get so sick of special right triangles. It's going to be great. Well, you're going to get even more sick. I've got a handful of problems for you guys to do this evening. This is basically the same style stuff you guys were doing yesterday. There are a couple of questions that did say labeled the reference angles, so just make sure you do that, because now we're going to kind of keep using that more. Just to the odds on here, I always like to have extras of these problems because a lot of people keep asking. So it's always better to have more problems than not. We'll go from there. Yeah, there's just a lot of a couple area things. Remember, for example, if I'm looking at number, this here real quick. If I'm looking at number 9 on this, well, actually, we'll look at number 11. If I'm looking at number 11, and it's asking me, oh, you give it him. It's asking me to figure out one positive and one negative coterminal of this. Is pi over 18 more or less than 1 revolution? Actually, rephrase. Is it within 1 revolution? Okay. Since it's within 1 revolution, all I have to do is add 2 pi and subtract 2 pi. But instead of adding 2 pi, what am I going to write it as? 36 over 18. Because isn't that 2 pi? I'm getting the common denominator, so I get 37 pi over 18. And if I do the same thing with the negative, I just want to make sure you guys saw that. A lot of these are super fast. It's just the idea that you put it in the common denominator. Don't switch back and forth between degrees and radians. That's just silly. Very, very silly. and you get 35. Okay. I said do the odds, right?
Yeah.
Okay. Yeah, they're real quick. They really are. Really, the ones that'll take you a second or two extra to do are going to be reference angles. That's usually the ones that take a minute to figure out. Remember, reference angles are always just how far are you off of the x-axis. Yep. Because it's within one revolution.
I see. She comes to